Close to 100% of anatomy and physiology students can tell you that anatomy is a study of structure and physiology the study of function. What we'd like to do in this video is clarify specifically what those words mean. So our objectives will be to define structure, define function, and we'd really like to talk about how structure relates to function and how that will be a consistent theme throughout this course. Almost 100% of anatomy and physiology students can tell you that anatomy is a study of structure and physiology is a study of function. That's probably related to the fact that they're told that that's going to be one of the first questions on their final exams. But even though students can pretty much always say those words, it's not clear that the students always understand what the words mean. So let's talk quickly about structure and function. Structure refers to the shape or composition of a system or a molecule of something that exists in our physical world. And function refers to a process, something like generating an electric current, regulating the type and speed of chemical reactions, or generating force and motion. So to demonstrate that, I created an electrical circuit. I hope you can see here we've got some batteries. The batteries are connected by conducting material, metal. And you can see that there's a light here. If I complete the circuit, then the light lights up. So this represents a change in shape. The shape of this circuit gives this system the potential to conduct electricity, which would be the function. And if I have the shape of the system as so, with the wire not connected, there's no electricity, but a change in shape leads to a change in function. I'll just buckle that on. And then the electric current will continue to flow. If I disrupt the structure of this system, say I take out a piece, so I've disrupted it, then it doesn't matter the shape change that I was initially talking about, there will be no current. Another important component of this system, though, is the composition. So if I have metal wires that are completing this circuit, I can conduct electricity. But on the other hand, if I take something like wood, I can do the same thing. I can complete the circuit, but wood doesn't conduct electricity. So the composition of these materials also relate to the function. Again, I'm just taking a different piece of metal, some wires. Shape. If the shape is such that electricity can flow, then we'll have an electric current. If the shape is disrupted or the composition is not what it needs to be, then there will be no electric current and we won't light the light bulb. Now let's talk about structure and function in the human body. A lot of people, when they think about anatomy and physiology, think about identification of muscles and how those muscles work with bones. So that's a reasonable place to start. Let's start with the human deltoid. This is a shoulder muscle. It has 3 heads, the anterior, middle, and posterior. All of these heads attach at the deltoid tuberosity on the humerus, but they have different origins. The origin of the anterior head is the distal part of the clavicle. The origin of the middle head is the acromion process of the scapula, and the origin of the posterior head is the spine of the scapula. With these different origins, contraction of the muscle will have different actions. Specifically, the anterior head, when it contracts, will flex the shoulder, and the posterior head, when it contracts, will extend the shoulder. Skeletal muscle tissue is organized in a similar fashion, irrespective of the muscle. And it's organized such that if a muscle fiber is stimulated to contract, it will generate force on an axis parallel to the muscle fiber. Like this bungee cord, if this muscle fiber were stimulated to contract, it would generate force only in the direction parallel with that fiber. On the other hand, by changing the attachment points of the muscle, we can change the action of the muscle. To use the analogy of the deltoid, with the anterior head of the attachment points, the origin is the clavicle, the insertion is the deltoid tuberosity on the humerus, and with those attachments, when the muscle fiber is stimulated to contract, it would cause the shoulder to flex. By changing the origin from the clavicle to the span of the scapula, like the posterior head, that same organization, same muscle fibers, when stimulated to contract, would cause the shoulder to extend. So using the skeletal muscle system, we've shown how changing the attachment sites of any given muscle will change the action, or changing the structure of the system changes the function. This is an example of the structure-function relationship at the level of organ and organ system. But remember, when we're looking at the human body, we look at structure from the atomic level up through the level of the entire organism. So whereas the skeletal muscle attachments in gross anatomy is an example at the level of organ and organ system, we can use a comparison of skeletal and smooth muscle to look at how structure at the molecular level affects cell structure and tissue structure and therefore function. Looking at skeletal muscle, the reason a skeletal muscle fiber contracts in a single direction is because the motor proteins that generate force are oriented such that they will tug only in one direction, causing shortening of the muscle. This is a molecular architecture within a single muscle fiber or muscle cell for skeletal muscle. When we look at smooth muscle, this is different. Within a given smooth muscle cell, the motor proteins are oriented such that they can generate force in a variety of directions. Okay. The end result is when smooth muscle contracts, the cell gets smaller, not only along the axis of the cell, but in all directions. The cell shrinks in width and depth as well as length. So because the molecular framework within a smooth muscle cell differs from skeletal muscle, when the cell is stimulated to contract, the structural changes within any given cell differ from skeletal muscle. But more than that, the tissue structure, the way each of the cells is connected to each other, is different when comparing smooth and skeletal muscle. In skeletal muscle, each of the muscle fibers or muscle cells is oriented parallel to its neighbor. This is shown in the upper left-hand corner. We've kind of seen this, where that cell is parallel to each of the neighbors. If we look at smooth muscle will often surround a hollow passage, and the layer of smooth muscle in this tissue is depicted in there. So you can see these individual smooth muscle cells oriented in a circular fashion. When each of those muscle cells contracts, the entire volume of the cell shrinks. What this means is when the smooth muscle contracts, the diameter of that hollow organ will decrease. So again, at the molecular level, because the orientation of the force-generating molecules differs from skeletal muscle, the generation of force differs. Therefore, when the muscle contracts, the structural changes in the cell is different. And because the organization of the cells is different in the tissue, the function of the tissue is different, where we're going to see contraction or a decrease in diameter of a hollow organ when smooth muscle contracts, as opposed to a shortening of a muscle along the parallel axis of the fiber with skeletal muscle. We've seen how the function of the skeletal muscle system is dependent on the structure, and that's at the level of attachment for each individual organ or skeletal muscle. We've also seen how muscle function is dependent on the molecular architecture within each individual cell, along with the arrangement of cells at the tissue level. What about at the atomic level? Even at the atomic level, the shape of a given atom or ion dictates its function. For example, both sodium and calcium are positively charged. When sodium enters a muscle cell, whether it's smooth muscle, cardiac, or skeletal muscle, there'll be an electric current. That's true for sodium and calcium. But when calcium enters the sarcoplasm, or the cytoplasm of the muscle cell, calcium will cause generation of force. Calcium will bind to specific proteins, cause a shape change in those proteins, which will then allow the generation of force. Sodium, even though it's a positively charged ion, has a different shape and doesn't induce those structural changes in the proteins and will not cause the generation of force on its own. At this point, I hope we've accomplished the goals of this video. We've defined structure as the shape and composition of any item with which we're concerned. We've defined function as a set of processes, whether it's generation of force and movement, regulating the rate and type of chemical reactions, generating an electric current. These processes are dependent on the structure of any given system, within the cell at the molecular level on up to the organ systems. So the processes depend on the structure within an organism, or function depends on structure, just as structure depends on function.